Welcome back everyone to 12.3. We're continuing the saga here of the dot product. And so the dot product is this great thing that helps us find really angles between vectors. That's really kind of its main use here. And so I'd like to start off by going over a theorem here that's very similar. It's theorem 3.1, but now that we actually have the defined dot product, let me go ahead and write it like this. So I'm going to use that notation here. So we have theta, again, the angle between two specified vectors, A and B. This is going to be equal to the arc cosine, or cosine inverse of, and we found last time that this should really be A dot B divided by the magnitude of A times the magnitude of B. That right there is going to be the angle between vectors. Equivalently, this is really the one that I memorize right here. If you're going to memorize one formula out of all of these formulas here, this is the one that I memorize. Right? So, okay, the dot product is equivalent to the magnitude of A times the magnitude of B times the cosine of the angle between them. And then it's very quick, right, to kind of get back here. You can solve this for theta if you'd like to go ahead and solve, right, if you want to know what theta is. But this right here is usually the one that I memorize, right, of all of them. So let's go ahead and do a little bit of practice with this, right? Let's find the angle between a few vectors here, right? So, okay. Find the angle. Again, I'm going to go ahead and I'm going to show you kind of using this one right here, right? Because there's always lots of formulas that you can memorize. Maybe you don't need to necessarily memorize them all, right? And so I'm just going to show you, if I only memorize this one right here, how we can still come up with all of the answers. So, okay, find the angle between the following vectors. So I'm going to go ahead and first calculate out A dot B. So again, we multiply the first components together. 1 times -1 would be -1. 0 times really anything is 0. And finally, 1 times 2, that's going to be 2. So A dot B, that's going to be 1. Let's also calculate out the lengths of these vectors, or the magnitudes of these vectors. So the magnitude of A and the magnitude of B. So the magnitude of A, that's going to be the square root of, and again, I'm looking at each one of these components, squaring it. So 1 plus 0 plus 1. Right, because these all have kind of boring squares, and we add those together and we get root 2. Okay, how about B, right? So if we square each one of these pieces, well, that's something a little bit more exciting, at least than A, right? So -1 squared would be 1, 3 squared would be 9, 2 squared would be 4. Add those all together and we get the square root of 14. So again, if I have just memorized this formula right here, I would say that 1 is equal to root 2 times root 14 times the cosine of the angle between these things. And right, again, this is what I want to find out. I want to figure out what is that theta. So I'm going to go ahead and divide each side. And again, square roots, really, these things are exponents, and exponents have lots of nice properties, and one of them is, right, if you have them multiplied together, you can kind of just smush these things together, and really you can just multiply the 2 and the 14, and that's going to give you 28. Again, that square root doesn't go away. You still have to include that there. So it's going to be the square root of 28. And notice I divided that because I'm interested in solving for theta here, right? I'm trying to solve theta. What is that angle? So my last step here would be just to take the arc cosine, or the cosine inverse on both sides, and we'd have cosine inverse of 1 divided by root 28. And this right here would be my final answer. I know it's kind of not a very satisfying final answer, right? But this is kind of as much as we can do without a calculator. All right, we have another problem. Again, this one's very similar. It's just in the IJK, right? The standard base notation here. Go ahead, pause the video, take, 5 minutes, work this one out on your own, and then we'll go ahead and spoil the surprise together. So again, pause the video, see how far you can get, and then we'll go over the results together. All right, so I went ahead, and while I had the video paused and everything, I wrote it out. So I'm hoping that when you went ahead and calculated these things out, the magnitude of A and B in the dot product, you got root 11, root 20, and 10. Then we went ahead and we used our theorem up here. And again, you can, if you have this memorized, right, you can kind of skip some steps a little bit here. But I'm just saying, well, let's manage our expectations, right? When it comes to quizzes and exams, and maybe we'll have a lot of formulas to have memorized, let's go ahead and just remember one of them. And I think this one's a bit more important. So we'll go ahead and memorize that. And so we assemble these correct pieces, right? The 10, the root 11, and the root 20 kind of into our formula here. And then I went ahead and I took an extra line here and really showed off, right, that we're combining these square roots. And so 11 times 20 was 220. And then I divided by that to isolate the cosine of theta. And again, we're trying to get theta equals, right? I want to know what is that angle between these vectors. And so I go ahead and in order to get rid of that cosine, well, I need to do the inverse, right? The cosine inverse on both sides. And so that's what gives me my final answer here, cosine inverse of 10 divided by root 220. All right, so that's some good practice on figuring out angles between vectors. And again, that's the main purpose, one of the nice things about the dot product here. Let's go ahead and move on and talk about properties, right? So again, anytime you get kind of some new operation, you have to wonder what kind of properties hold with this operation. The claim is for the dot product, darn near everything that you know and love, back from regular old multiplication, right? Regular old products of real numbers, these hold for our dot products of vectors here. So one thing that we usually like is the commutative property, right? It shouldn't matter in which order you multiply. And I'm glad to say that it truly doesn't, right? So A times B is the same as B times A. This is the associative property, right? So if you have C times A, right? And then you multiply that by B, this would be the same thing as if first you did the dot product between A and B, and then you did your scalar multiplication. Right, so you can kind of change the order up a little bit. You can distribute over dot products, right? So this would be the same thing as A dot B plus A dot C. And again, this is the dot product between vectors here. If you take 0 and dot it with a vector, you get out 0. And then finally, this is a bit of an interesting one here. If you take A and you dot it with itself, the claim is that you get the magnitude of A squared. So that's the only one that's a little bit strange. I will note also back here that this, right, whenever you do a dot product, you get out a number, right? It's not a vector, it's just a number. It's a scalar, right? So this 0 right here is not the vector 0, it's the scalar 0. So notice that this does not have the little arrow over it, right? I intentionally did not draw that, just like the C back here, right? This does not have the arrow over it. This is the scalar multiplication back here. So all of my things that should have arrows over it do. In this case, I was extra careful. And so, okay. Let's go ahead and go over the proof of one of these. We won't do the proofs of all of them, but again, anytime you have a mathematical theorem, there is a proof. And the textbook goes over a lot more of these and whatnot, but maybe we'll go over one of them. Usually when I ask classes, you know, which one do you want to go over from these? I guess usually the most surprising one is E right here, right? It's maybe not inherently clear where exactly that comes from. And so let's try maybe the proof of E in this case. Right, and see why this works out. So we're going to go ahead and start off exploring this left-hand side a little bit. And hopefully we will show that it's equal to the right-hand side. So again, A dot A is where we'd like to start off with. And I'm hoping that after a series of steps here, right, that we can make this at the very end of the day equal to, and this is the magnitude of A squared. Okay, so that's my goal here, is to try to connect these dots and try to show that the thing on the left is actually equal to the thing on the right. So let's maybe just kind of start exploring this a little bit. We're going to work our way forward, and then maybe we'll work our way back. We'll just kind of whittle away back and forth here until hopefully we meet at the middle. So, okay, the vector A, let's go ahead and if we want to do the dot product here, let's go ahead and write out some components, right? So I'm going to say A1, A2, A3 are the components of A, and we're dotting it with itself, A1, A2, A3. And so if I dot product these things, right, again, we're supposed to take the first component and multiply it by the other first component, which happens to be itself, right? So this is A1 times A1. Well, that'd be A1 squared. Next up, we take the second components, right? So A2. A2 times, this one also has an A2, so this is really A2 squared. And then finally, the third component's A3 times another A3. So A3 squared. So A1 squared, A2 squared, A3 squared. And we'd say, okay, this actually does kind of look like a magnitude to some extent. let's go maybe back here. If we were to say, what is the magnitude of something, and then we need to square it, right? The magnitude of A. Well, the magnitude of A would typically look like the square root of the first component squared, the second component squared, and the third component squared, all being added together, right? And now the last big thing, right, is that these squares and square roots, right? So we have this squared over here, and we of course have the square root right here, that these should perfectly cancel out, right? Squares and square roots should nicely cancel out, and so then you just get whatever is left on the inside. And on the inside, well, that's actually exactly what we have up here. So let's go ahead. I think we've connected the bridge actually maybe one step earlier than I was expecting. So let me go ahead and I'm going to cheat with using technology and move this up. I apologize for those of you who are not using tablets or whatnot. Maybe just draw an arrow or something like this. But let's go ahead and make sure that these all make sense, that we can connect the dots here. So again, the dot product here, we wrote out the components of A. We evaluated out the dot product. That was our next step. And then we decided, well, this is the same thing as, and it's kind of, right, this is a strange step that you maybe wouldn't necessarily think of, and this is kind of why working back and forth a little bit is sometimes nice, is introducing this square root and the squared, right? Because normally these things would have canceled each other out. But this right here is the same thing as the magnitude of A squared. So that's why this works out here. All right, so this is the proof of our E item, I suppose, in this previous theorem. All right, so again, all of these have proofs. I just decided to do one of them. The last bit here for this video is an application. One nice application of dot products is work. So quite often when you have a force vector, if it's acting on some particle, some object, right, it can do some work, right? And so if you have a constant force, there's this nice formula, and it's kind of, if it's heading exactly in the maybe the same, the force is acting in the same direction as your displacement, then the claim is maybe physics has given us work is equal to force times displacement. And so, right, but this is where force and distance are just numbers, right? And so you used regular old multiplication, right? They also had to kind of be in the same direction as each other. However, right, if you were to have a force vector, right, so not only a number but also a direction associated with this thing, and you had a displacement vector, right? How much did this thing actually move? This object actually move? Then the claim is you can recover a nice work formula, and now it is the force vector dot the displacement vector. So this is a nice upgrade for work. All right, so let's go ahead and try to do a couple quick problems related to this. The first one is, suppose you have the magnitude of F is 20 newtons, the magnitude of D, the displacement, is 5 meters, and the angle between the force and the displacement is theta equals 45 degrees. What is the work done by this force? So again, work is equal to force dot displacement. The problem is that I don't have vectors right now, so that's a bit of a pain. However, right, way back here on the first page, I told you, right, if you want to memorize one of these two formulas, the second one's quite nice, right? Because first of all, it's not too hard to solve for the first one here, but also it actually applies in more situations. So here's a situation where we don't actually have what the vectors are. We don't have F and D. But we should know that this is the same thing as the magnitude of F, the magnitude of D, times the cosine of the angle between them. That's back because of this theorem 3.5 at the beginning of the video. And these are things that we actually have. The force being 20 newtons, the magnitude of this displacement here being 5 meters, and the cosine of the angle between them, again, the angle is 45 degrees here. And so the cosine of 45 degrees is root 2 over 2. And so let's see, 2 times 5 times root 2 over 2. So a little bit of cancel out here, and we get 50 root 2's. And again, our units here were newtons times meters, so Newton meters. And this is kind of one of the common units for work here. Newton meters and foot pounds are the common ones. All right, so here's one example of finding work done thanks to our good old dot product formula that we have here. One more, we have a box is being pushed with a constant force of 1, 2, 3 newtons. So here we actually have a vector. How much work is done in moving the box from the point 1, 0, 1 to the point 2, 1, 1. And here, although I don't specify it, let's assume that both of these things, all of these have units of meters. All right, so we have what our force vector is. The only question is, what is our displacement vector? Right? So with the displacement vector, you can write down, again, kind of another formula if you'd really like, but I like to kind of think of it intuitively, right? So if you start at 1 and end at 2, right? I'm just looking at my first component here. The question is, how much were you displaced? How much did you move? Well, I think we moved 1. Right? So again, if you started at 1 and ended at 2, you had to take 1 step to get to 1, from 1 to 2. Likewise, if you start at 0 and end at 1, we had to take 1 step to get from 0 to 1. And then finally, if you start at 1 and end at 1, how many steps did you have to take? How much were you displaced? Well, you were displaced 0. You didn't move at all. So this right here would be my displacement vector. How much did we move to get from 1, 0, 1 to the point 2, 1, 1, right? Okay, so this is our displacement vector. So work, according to our formula, this is going to be F dot D, force dot displacement. We know our force is 1, 2, 3. Our displacement we've just calculated is 1, 1, 0. So when we apply this dot product, 1 times 1 is 1, 2 times 1 is 2, 3 times 0, well, anything times 0 is 0, and so we get 3, and again, the units here are Newton meters, right? Because this is in newtons, and I said assume that that one was in meters. So our final answer here is 3 Newton meters. All right, so that should do it for this video in 12.3. I hope you guys have enjoyed. I'll see you out there.